Hi, I'm Sean Orchuk with WEG Electric Machinery. In the following training modules, we'll discuss the details of a synchronous motor.
Here we have a synchronous motor. This is a much older model than you'll normally be working on, but it's ideal to show the different components of the assembly. This synchronous motor is an open type, which is why you can see the windings. This is not common on modern assemblies, which have to be protected for safety reasons. You can see that the bearing assembly is mounted on the end of the motor via a bracket. So this would be called a bracket-mounted bearing. This is in contrast to a pedestal mount bearing, where the bearing is located externally on its own pedestal and sole plate. Within the motor, we have a number of different components, and within the bearing assembly, and we'll talk about those in greater detail now. Now we can take a detailed look at the assembly. You can see that this stator is a random wound stator, which is unique to this specific motor, which is used for training purposes. You can see the individual rotor poles, often called salient poles, and this machine has 6 poles. Obviously, it's a 6-pole motor, so it will operate at 1200 RPM in the North American grid. You can see that this is a collector ring motor, or it's statically excited. This is in contrast to a brushlessly excited motor, but the rotor poles operate the same in either. You can also see that there are interpole connections. These are the cables in between each of the poles that pass the current from one pole to the other. And these are useful in doing a pole drop test and should be inspected because this is a location where a failure can occur. This motor has very simple blower blades, which you can see here are simple flat pieces of metal. Some motors that operate at higher speeds will have very complex radial blowers, and slower speed units will typically have a blower similar to this with a bent piece of sheet metal. We should inspect these blowers carefully to ensure there's no corrosion or problems with the fasteners or evidence of contact. Here we have a much larger synchronous motor, and we can talk about some of the components. You can see here that we have form-wound stator coils, which are very typical for medium and high voltage applications. You can see the individual poles here, and we can see the blower fan. This is a very low-speed machine, so the blowers are very rudimentary, in this case just flat steel plates. This machine has a pedestal bearing, which is mounted on its own pedestal and on a base, and that's in contrast to a bracket bearing, which would be mounted on a bracket to the machine. This is clearly the drive end of this motor because we can see the shaft protruding, and this would have a coupling or other device to connect it to the driven equipment.
This is a 6-lead synchronous motor. 3 of the leads connect to the line going back to the switchgear, and 3 of the leads connect to the neutral bar. You can see all 6 leads have been lifted as the terminal box is removed. Typically, you'll complete electrical testing with the terminal box installed, but all 6 leads need to be disconnected for an accurate test. Here we've got phase A, or leads 1 and 4, disconnected and connected to the red lead of an insulation resistance tester, and the black lead connected to a hard ground. Note that the other phases have been connected to ground using a bare copper wire. This is critical to allow both a phase-to-phase and a phase-to-ground test to be completed simultaneously and also to render the other phases safe. Once the polarity index and insulation tests are completed, ground the phase you're working on with a bare copper wire before touching it, and then carry on to the other phases. Record both the insulation resistance and the polarity index test results in the field report. Now that we've completed the insulation resistance testing, we want to measure the resistance of each phase. You can see here I have the 2 leads of a milliohm meter, sometimes called a digital low resistance ohm meter or DLRO device, connected to phase A, or leads 1 and 4. Many automatic testers will perform the same test, but the result is a resistive imbalance of each of the 3 phases. High resistive imbalance is typically resulted from poor lugs. You may also check the resistance back from the switchgear room, and that will tell you the resistance of the complete cable set, including the stator leads. Once we've finished electrical testing, let's spend a minute addressing the lead cables. Carefully inspect the lead cable for cracks, splits, or brittle parts, and check the flexibility of each cable. Take a lint-free rag and dip it in denatured alcohol and clean the cable, as this is a common cause of low resistance for the unit. Check the lug at the end of the cable and ensure that it's stiffly attached and properly protected. A high resistive imbalance in a machine is endemic of a poorly installed lug, so this is something to inspect for as well. Now it's time to perform collector ring maintenance. You can see that the main field leads have been disconnected from this set of collector rings, and now it's time to inspect the rings. Visually inspect the ring and ensure that there is a reasonable carbon film and no evidence of gouges or other defects. Take careful photographic measurements and inspect all around the rings. Check the spring tension on each of the brushes by pulling on the pigtail and ensure that the tension is the same. Use a spring tensioner if possible to get an accurate measurement and record this in the report. Remove all brushes by pinching the spring and pulling the brush out. Check the length of the brush and also inspect the wear face for any signs of foreign contaminants. If the brush has been severely depleted, replace it with one of the equivalent part number. Between the collector ring and the brush holder, there is a small gap, and this must be measured for all brushes. This distance is critical as too large of a gap will tend to cam the brush, which will cause chatter and early failure.
Let's talk about some of the details of the rotor assembly and some inspection parameters we want to have a real careful look at. Here we have one pole and another pole and another pole. And remember, the pole is what's used to synchronize the machine. This is what's operating while the motor is at synchronous speed. But around the pole, we have cage bars, and these are brazed into an end ring. Now, these brazed joints are susceptible to chemical attack or aging, so we want to have a very careful inspection of this area. You can see that this machine is nice and shiny red, and there's no evidence of oxidation. But if you see green powder or other evidence of rust or oxidation, we definitely want to take photos of that and add them to the report, because a repair may be required in the near future. Here we have the joint between two of the end rings through which the cage bars are brazed. This joint will pass a large amount of current during startup, several thousand amps, and is subject to a high amount of electrical heating. This assembly is bolted, which is actually not an ideal electric machinery style. Electric machinery tends to use a brazed joint, which is much better at conducting electricity. Carefully inspect this joint for oxidation, overheating, or separation of the joint, as this would dramatically impact the starting performance of the motor. Take pictures of any end ring segments which appear suspect.
Here we see the individual rotor poles installed in the stator core. Magnetic center is the ideal position where the rotor is perfectly centered axially within the stator core. To measure magnetic center, insert a TIG welding rod and touch the outermost lamination of the stator. Insert a second TIG welding rod and touch the outermost lamination of the corresponding rotor position. Pinch the rods together and remove. This will give you the relative distance of the rotor pole with respect to the stator iron. Duplicate this measurement on the other side of the machine, and that will determine any movements you need to make to achieve the best axial position. This is magnetic center for a synchronous motor.
The stator assembly is joined structurally with blocking. Blocking is pieces of felt or sometimes other insulating materials like G11, which are used to space the adjacent stator coils and also to structurally reinforce the overall assembly. Here we have pieces of blocking or felt which have been inserted in between adjacent stator coils, but there is no lashing which has been wrapped around it. Larger machines, especially high voltage and turbo generators, will have lashing which is wrapped around the coils, and that's used for extra reinforcement. Inspect all blocking for loose or missing blocks and take photographs of any which are not in ideal condition. This will be a future repair. Another important inspection point on the motor are the pole bolts. You can see here that there are studs protruding from this spider assembly upon which the rotor poles are mounted. Each pole in this case has one stud on each side, or two in total. Some motors will have 4 or 6 bolts or studs per pole assembly. These cannot be tightened in the field as they have a very specific torquing specification, but we absolutely want to inspect them for evidence of oxidation or looseness. Inspect every bolt around the assembly on both sides and record any that appear to be damaged or have oxidation.
The exciter rotor includes a 3-phase winding with 3 leads. Check the resistance using a digital low resistance ohm meter or micrometer between each phase and the insulation resistance from the phase to ground, which is the shaft in the case of the exciter rotor. Visually inspect the exciter rotor for any evidence of contact along the core iron or any evidence of damage in the end turns. The exciter stator is a DC field, and so there are 2 cables. Check the resistance across each and record the number in the report, and test the insulation resistance to ground from the 2 cables to a bare metal surface. Record these results in the field report. Perform a careful visual inspection of the inner core for any evidence of contact, as well as the end turns and lashing rings. For brushless synchronous motors, there is a wide range of diode wheel configurations. All diode wheels have 3 forward and 3 reverse diodes, as well as an SCR1 and SCR2, which is in parallel with an additional forward diode. Different control modules exist, but the main components can be tested using a simple fluke multimeter. Some diode wheels include a set of field discharge resistors, which may be spool wound, as in this case, or standard heater elements. After testing the diode wheel, perform a tug test on all the connections and ensure a sufficient number of cable ties have been used to secure the cables to the wheel. Let's take a moment now to talk about covers. Covers are typically made out of sheet metal welded together and installed with a manifold of bolts. A nut driver such as this one is a useful tool for removing and installing the bolts, but extreme care must be taken not to damage the threads when we reinstall the fasteners. Once the covers have been removed, check all the gasket material, and any that's become damaged or embrittled should be replaced. Neoprene or Viton is an adequate material for virtually all synchronous motors, and typically the thicknesses range from 1/8 to 3/16 of an inch. Once you finish reinstalling covers and gaskets, apply a bead of RTV on all upper surfaces, such as the air seal shown here, to prevent water from migrating into the motor. Now let's talk about filters. Some rotating equipment is installed with WP1 or ODP covers, which don't have any filters and have only a set of screens. These can be quickly inspected and cleaned as necessary. This is a weather-protected 2 or WP2 enclosure, and so it has an array of filters. We remove the cover and inspect the filters. In this case, we're using paper filters. If the equipment is installed with stainless steel filters, they can be cleaned with compressed air or steam as necessary and reinstalled. These paper filters should be discarded and replaced at any outage. Another common problem with enclosures and covers is the gasket material. When removing different covers, it's common for the gasket material to stick, some on the motor and some on the cover. If the gasket material tears, replace it with neoprene or Viton. If the gasket material is in good condition and is simply peeled off, use some spray adhesive to reattach it to prevent leakage into the machine. It's always preferred to use hand tools when installing and removing covers, but if you're going to use power tools, don't hammer on the fastener, as this will damage both the gasket material and the threaded fastener. Simply go until the driver clicks, and then use a hand tool to finish up. That's sufficient to tighten this panel cover.